Hi there, Mr. Sutton bringing you the AB Calculus 6-2 classwork solutions on separable differential equations. For this problem, I'm trying to find essentially the solution to this differential equation with the initial condition 0, 5. So the first thing I notice is I have a y in the differential equation, an output variable. That tells me I need to separate my variables in the beginning. So I'm going to divide both sides by y. That'll be dy over y or y to the negative 1 dy, either of those. And then on the right side, I'm going to multiply dx to get that over there. So I've got secant squared x times dx. Next, I need to take some antiderivatives. On the left side, this is going to be ln absolute value of y. On the right side, I've got conveniently just tan of x plus c. Now I need to plug in my initial condition. So I've got ln of 5 here, and then tan of 0 plus c. Well, tan of 0 is just 0, so this is really just c equaling ln of 5. Next, I'm going to plug that back in, but I have to resolve this absolute value before I do that. Since I have a y value of 5 in my initial condition, that tells me that this y inside here is positive, which means I don't actually need the absolute value at all. So I'm going to write then just ln of y equals tan of x plus ln of 5. And now I just have to isolate y. I can do that by raising e to both sides here. So that's going to be y equals e to the tan of x plus ln of 5. All of that's going to be in the exponent. And you'll notice that doesn't match any of the answer choices. That's because this ln of 5, you can actually split this off so that you have e to the tan of x times e to the ln of 5. And e to the ln of 5, the e and the ln just cancel, leaving you with a 5 that can be the coefficient on this other e term. So when the dust settles then, we have 5e to the tan of x, which is going to be choice C. For this problem, the temperature of a solid is modeled by some non-constant h function increasing according to this differential equation here. And this is measured in degrees Fahrenheit, T is measured in hours. Which of the following has to be true? So they're talking about, well, what h equals, and then they've got, it looks like these are kind of like different steps in the process of solving a differential equation. So why don't we just go ahead and start solving this until we get something that looks like one of these answer choices. All right, so my first step, they were actually kind of nice to me here. They didn't give me any t's to mess around with, just this 2h plus 1 over here, but we do have to be a little bit careful. It's very tempting to just integrate both sides and call it a day. However, this is an output variable, this h, so that means that I have to use separation of variables in order to actually differentiate, or integrate this rather. Now you might be wondering, well, how do I get this h to be with the dh? I'm going to divide both sides by this entire 2h plus 1 thing right here. That's going to leave a 1 over on the right side, and it's going to bring the expression with the h in it down below the dh on the left side. So dividing both sides by 2h plus 1, I've got dh over 2h plus 1 equals, well, now there's just a 1 left over there. I'm going to multiply dt over there to be with it. All right, this is none of the answer choices. Let's keep going. The next step is going to be to take the antiderivative of both sides. On the left side, this is kind of an ln sort of situation, but since I have an inner function with a tail of 2, I'm going to have to divide by 2. So this is going to be 1/2 ln of 2h plus 1 in absolute value. And then on the right side, I've just got t plus c. Is this any of my answer choices? Not quite. So we can either keep going and see if we can manipulate this to look like an answer choice. Now, you'll notice that 3 out of these 4 answer choices have an ln with no 1/2 out in front of it. So what would I have to do to get rid of this 1/2 and match one of these choices? Well, if I multiply both sides by 2, I would have just ln of absolute value 2h plus 1 equals 2t plus, I could call this 2c, but when you get down to it, this plus c is just some kind of unknown random constant that we haven't even bothered solving for yet. I mean, it's not, if I write c again, it's not technically going to be the same c because I just multiplied it by 2. But we don't have to write 2c. The way this thing works, you can actually just keep it as a c, and if we need to solve for it later, we will. So this ends up matching answer choice D then, and we're going to call it a day. For this problem, we want the solution to the differential equation dy over dx equals 5y squared with this initial condition. So we're going to start by separating variables because I have a y in my differential equation, an output variable. So I'm going to start by dividing both sides by y squared. That gives me dy over y squared, or y to the negative 2 dy, same thing, equals, well, I'm going to multiply the dx over to the right side, so that's going to be 5 dx. Now I have to take the antiderivative on both sides. So on the left side, this bumps up to a negative 1. Dividing by that, I've got negative y to the negative 1 equals, this is going to be 5x plus c over on the right side. At this point, I have to plug in my initial condition to figure out my c value. So I've got negative 3 to the negative 1 over on the left. On the right, I've got 5 times 0 plus c. So this is really just c on the right side because that 5 times 0 zeroes out. So what does c actually equal? Well, over here, this is going to be negative 1/3. So there's our c value that we have to plug back in. Plugging that back in, I have all of this stuff in the general solution minus 1/3. And at this point, I have to isolate y. It's almost there, but we have a negative to take care of. We also have this negative 1 power. I'm going to take care of the negative first. If I multiply both sides by negative 1, I can write this as negative 5x plus 1/3 or 1/3 minus 5x, either of those. And then if I raise both sides to the negative 1 to get rid of this negative 1, that's going to end up giving me 1 over all of this stuff down here. Now, I don't see anything that looks like that in the answer choices, so before I actually take the reciprocal of both sides, I'm going to merge this into one big fraction. For that, I need a common denominator of 3, so that means this would be 1 minus 15x all over 3. And now that I've got just one big fraction, I take the reciprocal, so y equals 3 over 1 minus 15x. Is that an answer choice? It is. Choice D. For this problem, we're trying to find the solution to this differential equation with the initial condition down here. So to start this off, I notice that I have a y in the differential equation, meaning I have to separate my variables because that output variable's in there. So I'm going to start by dividing both sides by y. So I'll have dy over y. And I'm not dividing by 2y. I'm just going to keep the 2 over there. It's actually going to end up working out better. In general, I like to move as little as possible over on the y side. So now that means dx is coming up here with a 2. So 2 dx over 2x plus 1. And now taking the antiderivative on each side. The left side's pretty easy. That's just ln of absolute value of y. On the right side, we have ln absolute value of 2x plus 1, but we have a tail of 2 in there, an inner derivative of 2. So we're going to have to divide by 2, but there's already a 2 here. So conveniently, this 2 gets divided by a 2 and the 2's cancel, leaving us with just ln of absolute value of 2x plus 1 plus c. All right, so now we use our initial condition to figure out what c is. So I plug in e for y, and for x I've got 0, so ln of absolute value 2 times 0 plus 1 plus c. So inside here I've just got 1. ln of 1 is 0, so the c just equals the ln of e, which is 1. Plugging that back in here, I'm going to have to resolve a few absolute values as well. I notice that my initial y value is e, which means that y in here is positive. So I'm going to write ln of just y. I don't have to make it negative y or anything crazy like that. For this next one, I have an initial x value of 0, which means that 2x plus 1 is going to come out positive. So I can also just use a parentheses on this one. I don't have to negate anything. So this is going to equal ln of parentheses 2x plus 1. And don't forget to add that c value of 1. At this point, we just isolate the y value. I'm going to do that by raising e to both sides. So I have y equals e to all of this stuff. And of course, that doesn't look like any of the answer choices. So let's dig a little bit deeper here. I mean, it kind of looks like, I don't know, maybe A or B, who knows. So one thing I can do, since things are being added inside the exponent, I can split off this little plus 1 as an e to the 1 that's being multiplied by e to the ln of 2x plus 1. And now that I have just an ln in that exponent, the e and the ln cancel, So this is actually going to be e times parentheses 2x plus 1, which, if I distribute it, we end up with 2ex plus e, and that matches answer choice B. For this problem, I'm given this differential equation, and I want a solution if I have an initial condition of 0, 1/2. So I'm going to have to start by separating variables because I have an output variable, y, inside the differential equation. I'm going to move this e to the 2y up to be with dy, and then I'll multiply dx over to the other side to be with the 3x squared. Anti-differentiating both sides now. On the left side, this is going to be 1/2 e to the 2y. On the right side, this bumps up to a power of 3. Dividing by that, we have just x cubed plus c. Now I'm going to plug in my initial condition. So I have 1/2 e to the 2 times 1/2 for that y value equals x value of 0 cubed plus c. Over here, this is really e to the 1 power. So this is just 1/2 e, or e over 2, either way. So, and we just have c on the right side because 0 is gone. So c is going to be half of e. Plugging that back into the general equation here, we have 1/2 e to the 2y equals x cubed plus 1/2 e. And all that's left at this point is to isolate y. So first step in doing that, I'm going to multiply by 2. So that's going to be 2x cubed plus e on the right side, and e to the 2y on the left. Next, I have to get rid of this e, so I'm going to take the log of both sides. That gives me 2y on the left side and ln of all this stuff on the right side. And then finally, I'm going to just divide by 2. So that ends up being a final acceptable answer. For this next part of the problem, they want the domain and range of the function, which I'll repeat here, that we just found in part A. So let's do the domain first. Domain, you're asking essentially, what could I plug into this thing to break this function? And the only parts of this that have discontinuities in them is this ln part. We know that ln is not defined for 0 or negative numbers. So that means for our domain, this 2x cubed plus e stuff in here needs to be positive, needs to be greater than 0. But that's not enough. We have to isolate x when we're talking about domain. So if I subtract e, divide by 2, and then cube root everything, negative e over 2 cube rooted, x has to be greater than that. That is our domain. For the range, we're talking about what kind of values can this thing achieve for y values. So in general, normally for ln of x, our range is going to be all real numbers. ln grows very slowly, but it will eventually hit any y value you want if you go far enough to the right. And if you go close enough to the y-axis on the left, you can get down to any negative y values. So is this going to be limited by anything? Let's look at the inputs here. Are there any inputs that are off limits for this 2x cubed plus e? Well, we can go as negative as we want. We can plug in 0 here. We can go as positive as we want. Because we have an odd function, it goes forever in both directions. So because we're not limited inside here by this inner expression, that means ln can do its thing, hit all the real numbers. So our range for this whole function then is going to be all real numbers. On this problem, I'm given the differential equation negative 2x over y, and we're told that y equals f of x is a particular solution with the condition f of 1 equals negative 1, the initial condition. First part of the problem, they want us to write an equation for the line tangent to f at 1, negative 1, and then use it to approximate f of 1.1. So I'm going to use my tangent line formula. L of x equals f of a plus f prime of a times x minus a. In this case, since 1 is our launching off value, I'm going to write that L of x equals f of 1 plus f prime of 1 times x minus 1. We already know what f of 1 is. It's going to be negative 1. It's the y value when x equals 1. F prime of 1 we need to calculate using this differential equation up here. So if I plug in 1 for x, that means I'm using a y value on this one of negative 1. So this is going to be negative 2 times 1 all over negative 1. And then this is going to be, let's see, negatives cancel, so this is just 2. So over here now we've got the y value negative 1, that's what f of 1 is, plus 2 times x minus 1. Next we have to use this to approximate f of 1.1. So I can write f of 1.1 is approximately equal to negative 1 plus 2 times 1.1 now, plugging in for x, minus 1. We could leave it like this or simplify further. This is going to be, let's see, 0.1 inside, so this is 0.2, plus a negative 1 gives us negative 0.8. For the other part of this problem, of course, they want me to tell them the particular solution with this initial condition for this differential equation. Since I've got a y inside the diffeq, I have to separate the variables. So I'll start by multiplying y by both sides. So I have y dy on the left. On the right side, I'm going to multiply by dx to get negative 2x dx. And if I take my antiderivatives, on the left we've got 1/2 y squared. On the right, this bumps up to a power of 2, so this is negative x squared, because we have to divide by the 2, negative x squared plus c. Plugging in our initial condition, this is 1/2 times negative 1, the quantity squared, equals negative 1 squared plus c. Careful with your sign rules on this one. We know that this negative 1 and this negative 1 don't end up giving us the same thing. On the left side, this negative 1 becomes positive, so this is just positive 1/2. On the right side, this really is negative 1 because the exponent happens before the negative. So we have 1 that we're adding over to 1/2, which gives us a c value of 3/2 or 1.5, either of those. Now going back to my original, I just write all this, but instead of c, I'm going to write 1.5. And simplifying this now, because I have to isolate y, I'll multiply everything by 2. So I've got y squared equals negative 2x squared plus 3. And then I have to square root both sides, but I have to figure out, do I want the negative or the positive branch? Looking at our initial condition, we see that y equals negative 1 is part of that. So that means that in general, y is going to be negative for this branch of our particular solution, which means when I square root both sides, I need to write y equals negative square root of all this stuff.